Okay, welcome back to Discrete Mathematics. In this lecture, we're going to be talking about formal logic. And what is formal logic? Well, formal logic is a system of making statements based on logical premises. Logic is perfect for binary mathematics. In logic, there is exactly two values, true or false. False, we can assume takes the value 0, and true, we can assume takes the value 1. When discussing logical statements, we call each statement a proposition. Propositions are labeled with capital letters beginning with P. For example, the Earth is in space, we could call P. Mars is blue, we could call Q. And having fun yet is not a proposition because it does not have a true or a false value. Below, you'll see a truth table for P. There are two possibilities P could take, either true or false. Just like other mathematics, we can perform operations on these logical statements. The first such operator is the negation operator. Taking not P, we get Earth is not in space, and taking not Q, we get Mars is not blue. We add an extra column to the truth table to show not P, and we see that when P is true, not P is false, and when P is false, not P is true. Do note at this point in time, we are not making an assumption on whether the Earth is in space or not in space, we are simply listing the possibilities. Next, we have the AND operator. The AND operator takes two propositions and performs an operation on them. Here we can see there are four possibilities of combinations between P and Q. Either both are true, one is true and the other is false, or both are false. For each of these scenarios, we have an associated row in the P and Q column, which says whether P and Q is true or false for that scenario. Note, P and Q is true only when both P and Q are both true. Next, we have the OR operator. The OR operator is true whether P is true, Q is true, or both are true. It is only false in the condition when both P and Q are both false. If you're an English speaker, this may be a little confusing because you might be used to phrases like, you can have soup or salad, meaning you can only have one or the other. When we're dealing with this operation, that's called the exclusive OR operator. Here we see that the exclusive OR operator is true only when either P is true and Q is false, or when P is false and Q is true. In the final column, we see a complicated statement combining ands, ors, and nots that we have seen in previous slides. When we examine the truth table for this complicated statement and for the exclusive OR operator, we see that they have the same truth values under each condition. This means that these two statements are equivalent. Any time that a statement has the same truth table value as another statement, the statements are equivalent and can be substituted for one another. Next, we have the conditional operator. It's read P implies Q, or if P then Q. To give some examples, if I ate recently, then I'm not hungry. In this case, I am not saying whether or not I'm hungry if I have not eaten recently. And as such, P implies Q will be true when P is false. Similarly, if I'm reading 1984, then 2 plus 2 equals 5. If I am not reading 1984, then I am not saying that 2 plus 2 equals 5. Therefore, the statement P implies Q will only be false when P is true and Q is false. The last operator is the biconditional operator. This would be P if and only if Q. This statement says that P can be true if and only if Q is true, and also vice versa. This also means that if both are false, P if and only if Q is still a true statement, because neither P nor Q is true without the other one being true. Now, I will suggest that you please take a moment and pause, and so you can examine this truth table and understand what each of these operators does. Next, we'll discuss some vocabulary. A tautology is a statement which is always true, and a contradiction is a statement which is always false. For example, if we have the statement P or not P, we know that in either situation, whether P is true or P is false, that or statement will still be true. Therefore, P or not P is a tautology. Similarly, P and not P is always false, because a statement cannot be simultaneously true and false. Next, I'm going to cover DeMorgans Laws. DeMorgans Laws are two equivalencies which will actually be quite useful when you're programming. The first is not P and Q is equivalent to not P or not Q. The second is not P or Q is equivalent to not P and not Q. Note, for each pair of statements that are shown, the truth table values are equivalent. Please take a moment and learn these two equivalencies. Now it's time for a bonus slide. Let's consider for a moment the statement, If our country is poor, I will have no job. The converse of this statement is, if I have no job, then our country is poor. You will notice that this is not an equivalent statement. The inverse of this is, if our country is not poor, then I will have a job. This is also not an equivalent statement, but it is equivalent to the converse. The actual equivalent statement to the first statement is, if I still have a job, then the country is not poor. You will notice that many people are not aware that these statements are not equivalent, and they will casually use them interchangeably. Be aware of this and call them out on it. Finally, let's get to the useful part of formal logic, which is inference. When we're inferencing things, we start with statements that we assume are true, and then we try to make conclusions based on these statements. Let us begin by taking a truth table for P, Q, and P implies Q. We assume that P is true and P implies Q is true. Therefore, the situations where P or P implies Q are false, we will mark in red. After doing so, we can see that only one row remains, and that is the row where P is true, Q is true, and P implies Q is true. As such, we can see that there is only one possibility for Q, which is Q must be true. This is one way to make an inference. We will do the same thing on the right side of the screen using modus tollens. Let us start with not Q, and P implies Q. Since not Q is true, Q must be false, and since P implies Q, that must be true. Therefore, the only remaining row that is possible is where P is false. There are other named inferences which have all fancy Latin names, but none of them are nearly as important as these two, and these two aren't even that important to begin with. Now that we have mastered several operations that can be performed on true and false values, let us notice that these can also be performed on bits. As such, we can perform bitwise operations. Notice that traditional addition is not bitwise because each bit can affect the next one, such as in addition, we have carry. But when we use a bitwise operation, we simply pair up the bits from one number to the next, and they do not affect any of their neighbors. We can perform bitwise AND, bitwise OR, or bitwise XOR. Of importance is that when we are performing bitwise operations, both numbers must be the same length, and indeed, the output will also be the same length. That is all for formal logic, so please examine these practice problems that I've provided. Here we can see an image representing P and Q as a Venn diagram, with the shaded section representing P and Q. Please draw Venn diagrams for each of the equations on the left side of the screen. Finally, I recommend that you go make yourself comfortable with DeMorgans Laws.